Hello students, welcome back to the next module. Students, in the last two modules we have derived expression for kinetic energy and potential energy. In this module we will derive expression for total energy and prove that it is constant or conserved. So let's start with the expression for total energy. Students, we know total energy is the sum of kinetic energy and potential energy, that is T is equal to Ke plus Pe. Now, let's substitute the value of kinetic energy, which is nothing but half m omega square a square plus, and the value of potential energy is half m omega square x square. Now, we can very clearly see half m omega square is common here, and in the brackets we write a square minus x square plus x square. Now, minus x square plus x square can get cancelled, and therefore total energy becomes half m omega square a square. As we know, m omega square is k, force constant. Therefore, students, total energy can also be written as half k a square. So, equations 1 and 2 here represent the total energy of a particle performing SHM. Now, students, we clearly see the formula of potential and kinetic energy both contain x, and hence they continuously change. But if you look at equation 1 and 2, it is very clear that it is independent of x. Also, we know m omega square and a squares are constant. Therefore, I can say, students, total energy of a particle performing SHM always remains constant, or it is conserved. Now, let's move ahead. Now, as we know, omega is 2 pi f, omega square becomes 4 pi square f square, and students, total energy can also be written as half m 4 pi square f square into a square. Let's cancel 2 and 4, and total energy can also be written as 2 pi square m f square a square. As 2 and pi square are constant, therefore I can conclude total energy is proportional to mass of the oscillator. It is also directly proportional to square of frequency, and it is also directly proportional to square of amplitude. As we know, frequency is 1 upon T. The above formula can also be expressed as total energy is 2 pi square m a square upon T square. Here also T is proportional to m, T is proportional to a square, but I can write here Te is inversely proportional to square of time period. Now, let's prove conservation of energy in SHM. At any position x, we saw kinetic energy is half k a square minus x square, potential energy is half k x square, and therefore total energy, as we saw, let's substitute the value, which finally becomes half k a square. Now, let's check what happens at mean position. We know at mean position kinetic energy is maximum with the value half k a square, whereas potential energy is 0, and therefore, students, total energy at mean position becomes, let's substitute the values, half k a square plus 0, which is nothing but half k a square. Now, students, note equations 1 and 2 are same. That means total energy at any position and at mean position is the same. Now, but one striking feature here, very clearly we can see here Ke max is equal to the value of total energy. Very important for numericals. It is but obvious because potential energy is 0 at mean. Now, let's check what happens at extreme position. As we know, at extreme position kinetic energy is 0, potential energy is maximum, that is half k a square, and therefore, students, total energy at extreme position will become 0 plus half k a square, which is nothing but half k a square itself. And here we can very clearly see total energy is equal to P max. That means at extreme position total energy is purely potential. It was but obvious since kinetic energy was 0 at extreme position. So finally, from the three discussion, I can conclude that from equations 1 and 3, we can clearly conclude total energy of a particle in SHM at any position always remains constant or is conserved, but kinetic energy and potential energies are interconvertible, and one of the most important conclusions for entrance exams and numericals. KE max is equal to P max is equal to TE half K A square. We have proved this in the discussion. Now, students, let's go for graphical representation of the three energies in essential. So let's plot energy versus displacement. So very clearly we can see the three positions minus A, x is equal to 0 and x is equal to plus A. Now, as we know, total energy is same at all the points, that means does not change. So the graph of total energy will be a straight line parallel to displacement or x-axis. Now, we know at mean position kinetic energy is maximum, which is equal to total energy. So let's plot down the point. Whereas at the extreme position, students, kinetic energy is 0. You can clearly say this. Let us join the points and we get a curve that is nothing but a parabola. So the graph of kinetic energy versus displacement is parabola symmetric to y-axis. Now, we know at mean position potential energy is 0 and at extreme position it is maximum. Now, if I join the points again, students, it is again a parabola symmetric to y-axis. So let's finally conclude. So as I told, graph of total energy against displacement is a straight line parallel to displacement axis. The graph of potential energy and kinetic energy versus displacement is parabola symmetric to y-axis. At mean position, total energy is purely kinetic. At extreme position, total energy is purely potential. Whereas at other points, it is interconvertible such that the sum is constant, which is equal to half K A square. That's all in this module, students. See you in the next module.
अभिषेक सोनू जो भी आएगा अपने पास गाइड के लिए, यस